Hi, everyone. Thanks for joining us today. My name is Jennifer. I'm the marketing manager for Hioki and your moderator. This webinar today is on production testing of lithium-ion batteries. Since it usually takes about 3 to 5 minutes for people to log in and get situated, how about we do a quick polling? It's a fun polling, I promise. So we have put together some fun ice-breaking questions to get us all warmed up and get to know you all better. So let's jump right in. Let me see, here we go. You should be seeing these 6 questions in your screen about now. Please take a few minutes to go through these questions and answer them, and we'll share these in momentarily. And for those of you just joining us, welcome. We just started a quick polling, some fun ice-breaking questions to get us all started. So we'll give you guys about a minute or 2 to start voting. And after 2-3 minutes, we'll go ahead and stop the polling and share the questions, share the results. We're really curious to know the answers to question number 2, because most of us are working from home and we all have our own ways of being comfortable while we work. I see my husband working from home, and through his Zoom meetings he has business on the top and casual on the bottom, which I thought it was pretty funny. So I think we can all attest to that. I see answers coming in. I'm going to give you guys 1 more minute and then we'll wrap up and share the result. I do see some familiar names coming through. Hi, Angela. Hi, Bruno. Hi, Dio. Welcome back. Hi, Manny. Owen. Good to see you guys. All right, I'm going to end the poll in 20 seconds. And share the answers with you. All right, end the polling. And here are the results. So question number 1 was, where are you working from? Looks like most of you guys are still working from home. That's great. And head on heart, are you wearing PJs right now? It looks like most of you guys are still in PJs. Thanks for your honesty. Oh, actually, never mind. You guys are never wearing PJs. You guys are back to work gear during the work hours. Understand. Question number 3, in 1 word, how would you describe your past week? It looks like most of you guys had a great last week, some long weeks for some of us. Question number 4, why did you decide to attend this webinar? You wanted to learn new things. That's great. And some of you guys wanted to network and because your boss made you. Question number 5, what is your current role? Most of it looks like we have a lot of engineers in the house. We have a few contractors, consultants, and quite a few others. And last question was, where was Hioki founded? Looks like most of you guys answered it correctly. Yes, we were found in Japan. So I'm going to stop sharing. Next slide, please. So I want to share a little bit about our company. We were founded in 1935 in Japan, and we have been at the forefront of electrical manufacturing industry, providing the finest electrical test and measuring instruments through advanced engineering and innovative technology. And we're very proud to say almost everything is engineered and manufactured in Japan. We really strive to provide valuable and efficient solutions to meet the needs of our customers work in research and development, manufacturing, and electrical maintenance with conscious focus and quality and safety. Next slide, please. So here's a little bit about how we'll be spending the next hour. First, we'll start with the introduction of our speakers and our panelists. Then we'll move on to the presentation, which will take about 15 minutes, and we'll end it with a short Q&A session. Which may take about 10 minutes or less. And in terms of housekeeping, we'll have 2 panelists monitoring the Q&A box, so feel free to send in your questions and they will be answered. If not right away, then we'll make sure to get back to you with an answer via email. And we'll also make sure to share some of these questions that came through the box during the actual Q&A session. So with that said, we will not be stopping during the presentation to answer any questions, and we will not take any pricing related questions here, but you can reach back out to us separately and we'll be more than happy to assist you. Next slide. Okay, fun part. Now let's meet our speakers. We have Chris Schultz in the house. He is our product manager at Hioki, and he comes with an impressive background. Right before joining our team, he was a product manager with RNS, where he was responsible for Vector Network Analyzer product portfolio. Chris holds a PhD degree in electrical engineering and a master's degree in aerospace engineering from Georgia Institute of Technology. Our second speaker is Isan Daljik. Isan is an application engineer for Hioki and comes with 21 years of experience in engineering field. Before joining our team, he was a semiconductor test engineer too with Maxim Integrated and an application engineer with DFW Test Inc. Our third speaker is Sandro Barbaresso. Sandro is our application engineer and he comes with 25 years of industry experience in the electronic world. Before joining Hioki, he was a test engineer at the Texas Instruments. And lastly, our panelists, we have Fumiyagi Yagi and Tomohide Kusaki. Both are our application engineers and they will be answering your Q&A questions. All right, now without further ado, let's please welcome our first speaker, Chris.
Hey, Jennifer, thank you very much. Let me get to the next slide. So I'm Chris Schultz. I'm gonna walk you through the technical part of the presentation here. And if I can get the next slide, yeah. So here's the outline of what we're gonna talk about. That's the second part of a series of battery-related webinars. In this part, we focus more on the end-of-line testing. There are a bunch of tests that you're required to do or that you need to do to characterize batteries. So we're talking about assembled batteries. Specific tests are resistance tests. We've got a variety of resistance tests that we will mention and show you what the difference between the different tests are and when to use which one. We'll also talk about, and that's very important, about ways to minimize measurement errors for these tests, because you're talking about very low values, very low absolute values that you're testing. Next, we'll talk about the end-of-line testing. So this is for assembled batteries and battery packs. Very important, obviously, we're talking about why you need to do end-of-line testing, what the criteria are, and how you can get to high throughput and still very accurate measurements. And the third part of the presentation is going to be about automated test equipment, where accuracy is super important, but also throughput. The test time in testing, in production testing, time is money. How do you get to fast throughput without sacrificing accuracy and precision? So with this, let me just really quickly review the major applications of batteries. There's, of course, anything related to automotive and transportation. Starter batteries have been in cars forever. They usually use lead acid batteries. That's probably not going to change in the near future. You need a very high current to get to crank the starter motor. But everything else in electric cars has been migrating to nickel metal hydride batteries. There's a big push right now to migrate to lithium-ion batteries for reasons that we mentioned in the last webinar, primarily weight and power density. The second major application of batteries is anything that's mobile, that's handheld. Cell phones have been using lithium-ion for many years. A big part of a cell phone or an iPad or a personal device is the battery these days. So lithium-ion has been in that application for quite some time. We see more and more body area networks. Those are all sort of sensors that monitor the health of a body, especially with pandemics going on right now. So I would expect that we will see a lot more of that. Lithium-ion batteries are clearly the favorite for this application. And then there's the application of stationary power and backup power. So the typical case that I'm showing you here is a wind power plant. The wind doesn't blow all the time, so you need to buffer the excess energy that's generated and release it to the distribution network when there is a demand for it. Same thing, obviously, for solar cells. The sun shines during the day, and the usage is very often during the night. Traditionally, that's the domain for lead-acid batteries. We have a webinar coming up in 2 weeks that's specifically about lead-acid batteries. But NiCads have been used there with environmental issues, of course. And there's a strong push that's very well documented in the popular media right now towards lithium-ion batteries. Just a few numbers here on where the industry is and where the industry, or some analysts think the industry is going to go. The bottom of the curve here, these turquoise bars, that is all related to transportation. So within a few years, year 2023 estimate is that almost 60% of all lithium-ion batteries will go into automotive transportation. You know, the orange part here is for electric buses. So a majority of all the applications will be in transportation. And we're talking about gigawatt hour now, not the number of cells being produced. A lot of cells in cell phones, but at much lower power density. So we talked about the battery manufacturing process in the previous seminar. We talked about the earlier stages of the manufacturing process, specifically slurry. How do you detect the constituents of the slurry? How do you measure electrode sheets? How do you measure that the distribution of electrode sheets is constant or consistent? And how do you characterize the impedance of electrode sheets? We have very specialized tools for that. We talked about tap welding, so we're talking about nano-ohms or milliohm measurements with nano-ohm accuracy to make sure that the taps are welded correctly. We talked about insulation testing of the battery cells themselves before they get filled with electrolyte. In this webinar, we're mostly focusing on the end-of-line measurements. This is measurement of assembled cells, specifically internal resistance measurements. We have different methods to accomplish that goal. And then we're going to talk about the testing of assembled cells before they go to the end user. So with this, I'd like to do the first poll. There we go. If you can get this up here, thank you much. So in your opinion, what is the battery technology of the future? What battery technology will be most popular in, let's say, the year 2030? What's your vision for 2030? Is that lead-acid batteries? Is this lithium-ion batteries, fuel cells? Or is that a battery technology that hasn't been invented yet? I'll give it a few seconds to fill this in, so please put your answers in. And there's a lot of research going on in batteries right now. Okay, I still see answers coming in. All right, well, thank you very much. So the answer here is certainly not lead-acid batteries. So the consensus of the audience is that lithium-ion batteries will be the dominating battery technology in the next 10 years, so up to the year 2030. Some of you are bullish on fuel cells, and others believe that 14% actually believe that there's a technology that has not been invented yet. Well, thank you very much for participating in the poll. With this, I want to pass the word on to Ishan. He's going to talk about the specific measurements of assembled batteries. Ishan?
Oh, thank you, Chris. Thanks everyone for attending. I'm going to talk about cell testing, specifically grading of cells, lithium-ion cells, and the end-of-line testing, EOL testing. And hopefully we'll have an understanding of what the difference is and what requirements are needed for these two very different test steps. First of all, why are batteries sorted or graded? Well, As part of quality control, we have performance differences that exist between the cells. Even with the most stringent of manufacturing processes, there's going to be some variations, for instance, in the internal resistance of the cells. When those cells are incorporated into a battery pack, the ones with the highest resistance tends to heat up more than the other ones. And as they heat up more, the excessive heat accelerates the deterioration process. So they end up with an even higher internal resistance after multiple charge and discharge cycles. So whatever differences that you had to begin with are magnified with repeat charge and discharge cycles. And what happens then is the lowest capacity cell ends up reducing the capacity of the entire battery system, because battery management circuitry tries to maintain some kind of evenness, even capacity between the cells. So cell selection extends the service life of the battery by closely matching the cells that are used within the pack by capacity. And also higher grade cells may be reserved for special applications, or they could be sold for a higher market price, for instance. So to really understand cell sorting, we have to have some basic understanding of the electrochemical processes that take place inside the lithium-ion battery. And on the diagram on the left, it shows we have the negative electrode and positive electrode and the electrolyte in the middle. And you can see that the transfer of lithium ions from the negative to the positive electrode, they go through various different steps. If we look at the electrochemical processes for going from slow to fast, the slowest process usually is the lithium ion diffusion within the electrode, and this can be observed at frequencies of less than 1 hertz. As we speed up, the faster reactions are the charge transfer reactions, and they occur between 1 hertz to around 1 kilohertz. But the fastest reactions within the system, the battery system, are the lithium ion migration within the electrolyte, and they can be observed at frequencies of 1 kilohertz and higher. In this slide on the left, we have what's known as a Nyquist plot, or co plot, and it's essentially a plot of the components of impedance, the real and imaginary components of impedance. Except you'll notice the x-axis is the real resistance component, and the y-axis is the negative of the reactance. And going from right to left, the frequency increases. So if we look at and this is known as the electrochemical impedance spectroscopy. So if we look at the lower frequency range, what we see is the lithium ion diffusion within the electrode, and it's highlighted here in the pink box, and we use the term W for that. And as we get into the faster reactions, we have the lithium ion charge transfer reactions, and they're the semicircle section in the middle area between 1 kilohertz and 1 hertz. And finally, we have the lithium ion migration within the electrode, which occurs at 1 kilohertz and higher. On the right is the Randall cell model. This is a very basic circuit model that tries to describe what happens within the lithium ion battery. The two resistive elements here correspond to the lithium ion migration in the electrolyte and the lithium ion transfer reactions. And W is the Warburg impedance. It's not a standard resistance, but there's a formula that describes it. And we have this 45-degree angle, that's part of the response. And also the battery incorporates what typically appears as a double layer capacity or capacitance. And so the battery impedance is not linear. So there's 3 distinct regions which can be observed within the Colco or Nyquist plot. So this is a very valuable tool in order to really understand what's going on internally in the battery. There's 2 main methods of measuring the internal resistance of a battery. The first method is the DC-IR measurement. This is where the battery is discharged at a constant current and voltage is measured at specific times. The benefits of the DC-IR measurement is that it can evaluate characteristics with using an actual load and can evaluate reaction resistance. Some of the issues with it, obviously there's some problems with it, is that it requires preliminary charging of the cells. And that process can take up to an hour depending on the capacity of the cell. And timing is also tricky because the way the DC-IR, the DC resistance is defined is the change in voltage over the change in current. And we can see from the diagram here, the change in current is simply a step function. However, the change in voltage, it's time dependent. So your delta V is going to depend on when exactly you take the measurements. So that's why the timing is tricky with this method. And as a result, the measured values can exhibit a lot of instability. And also there's the requirement for complex equipment. And up to 100 amps or more may be needed for when testing large batteries. On the other hand, there's also another method called the AC-IR measurement method. And in this case, we use an alternating current to measure the impedance. And this allows for a more detailed examination of the internal resistance of the battery. For instance, if we look at the battery model here on the right, at very high test frequencies, the capacitor here is essentially, the impedance of it drops so low that it's essentially a short. So the majority of the current takes this path along R2 and through the capacitor. So at very high frequencies, we can evaluate R2, which is the lithium ion migration in the electrolyte. And at very low frequencies, this is known as the low frequency AC-IR method. At very low frequencies, the capacitor ends up blocking the majority of the signal. As you know, a capacitor will block DC and it has a very high impedance for low frequencies. So the majority of the current flows through R2, R1, and the W element. So when testing a battery with low frequency AC, it is kind of similar to measuring with DC. But as I'm going to explain in the next slide, there's actually some distinct advantages of using low frequency AC versus DC. And some of the advantages of the low frequency AC versus the DC-IR method is that it doesn't require preliminary charging. When you have a full cycle, you know, you go through a charge cycle and then followed by a discharge. So as long as your start and end points are the same within the cycle, there's no charging of the battery. So no preliminary charging is necessary. It has typically much faster test time. Test time that was 20 minutes maybe boiled down to 10 seconds. Also increased stability and repeatability of the results. And much lower current is required. What would have taken 100 amps with the AC-IR low frequency may only take 1.5 amps. And so this is a viable alternative to the DC-IR method. Now I'm going to talk about how do we measure the resistance or impedance. And typically for low resistance values, we force a current across a target and we measure the voltage across the target and calculate R with Ohm's law. This diagram here shows a setup using 2 wires. And the problem here is that the voltage drop across the target, which is Vx, is not exactly the same as the voltage that's measured by the voltmeter, because we have a current flowing in this circuit, and the resistance R1 and R4 represent the contact resistance and also the test lead resistance. So they cause a an IR drop. So this is not an accurate way of testing. Now, the solution to this, it's been around for ages, obviously, is the 4-point probes method, which uses an additional circuit or additional loop connected to the voltmeter. The sense voltage is measured using a different conductive path. So the current goes through R1 and back out through R4. However, the voltage measurement is done with a different set of probes. So typically the outer probes would force the current, outer meaning the distance between the target and the probe tips, and the inner probes are used to measure voltage. And so within the voltmeter loop, the current is essentially zero because voltmeters have a very, very high input impedance. So as such, when the current is essentially zero, the measurement, the drop across, that's measured by the voltmeter is essentially the same as the drop across the target. So that way, we're able to essentially cancel out the IR drop due to R1 and R4. And R2 and R3, which is the resistance of the voltmeter leads, is essentially irrelevant because when the voltmeter doesn't draw any current. Now, there's some issues with the 4-point probes method when you use AC test current instead of DC. And as we know, with an AC test current, we have a change in the electromagnetic field. There's an inductive field that's rapidly changing, and this can induce an EMF or a voltage on the voltmeter loop. And this EMF that's induced in the voltmeter loop adds to the voltmeter's readings and is an error. And for measuring minuscule impedances, we typically need a lot of current to be able to get a good signal to noise ratio. And as high current generates a lot of magnetic flux, this increases the error at the voltmeter. One way of solving this problem is referred to as the 4-terminal pair method. And the only difference here is that the force and sense lines are shielded with coax, and the return of the measurement current, the measurement current is returned back in the opposite direction through the coax shielding. And so what that does is that because it's carrying it in the opposite direction, it cancels the inductive field. And so by this method, we're able to take super low impedance measurements of less than 10 milliohms using AC. Here we have an experiment set up to demonstrate the effectiveness of the 4-terminal pair method versus the 4-terminal method. And picture number 1 on the left shows the Oki BT4560 battery tester, and it's connected to a 0-ohm dummy load. And as you can see, the sense lines or the connections to the voltmeter are they're placed far apart from the current carrying conductors. And in this setup, we compare the 4-terminal pair against the 4-terminal method, and the meter is zeroed out. And once the meter is zeroed out, you can see the differences between the two methods are essentially, they're non-existent. In the second picture, we bring the current carrying lines closer to the sense lines. So there's more EMF that's induced into the sense lines. And as you can see with a 4-terminal pair method, there's virtually no difference in the measurements. It hasn't shifted from the 0 point. However, with the 4-terminal method, you can see that there's clearly error that's being induced on the sense lines. And in the third picture, we bring the force and sense lines even closer still, and we place them on top of each other so that the more EMF is generated in the sense lines. And as a result, we can now see a significant difference between the two measurement methods. And this can be an issue because when you have cables, and for instance, in a production environment, it's very difficult, to be able to not change the placement of them. That's one of the things that, you know, we may not have control over. So this is one advantage of the 4-terminal method for measuring very, very low resistances. Now I'm going to talk a little bit about the battery tester requirements. So an ordinary resistance or an impedance meter can't really measure batteries because the batteries have a bias. And in order to select a battery tester, we need to understand what is our process step or what is our goal. Are we trying to have a deep understanding of the characteristics of the cell, for instance, with cell sorting? So are we doing characterization, or are we simply doing an end-of-line testing, which is, you know, the product has already gone through all the test flow and this is the final step. So another concern is what's the maximum open circuit voltage? Like, what's the maximum voltage that our battery tester has to measure? And with individual cells, I mean, 5 volts is plenty. But, you know, when you have battery packs with many, many cells connected in series, that can be an issue. So this is something that needs to be addressed. And also, what's our target resistance? And as our target resistance decreases, our test current requirement increases. And this is because of basic signal to noise ratio issue. We want to have a good signal to noise ratio, so we require larger test current. So for grading of cells, open circuit voltage of 5 volts is fine. And the ACIR method is typically used. And we want to be able to do a frequency sweep, use a wide range of frequencies in order to generate a Nyquist plot so that we can really see what's going on inside the cell. And 4-terminal pair method will give us the precision for that. And now for end-of-line testing of cells, again, for individual cells, 5 volts is okay. But for battery packs where you have series of cells connected, we may need more than 5-volt requirement. And in this case, we also use the ACIR method, but it's done at 1 kilohertz or a single frequency typically. And 4-terminal probe method is generally sufficient for this purpose. Of course, speed and multi-site testing are always desirable in any kind of production test, whether you're doing grading of cells or end-of-line testing of cells. Now I'm going to talk a little bit about the internal resistance, voltage, and capacity of lithium-ion cells. And here's some information that I was able to glean off the internet from some data sheets. And they show different lithium-ion cells. The top one, for instance, is 170 milliamp hours, and internal resistance is about 250 milliohms. And the one below it is 2,600 milliamp hours, and the internal resistance drops to about 70 milliohms. And as we go down further to the last one here, it's 5,000, it's over 5,000 milliamp hours, and the resistance is less than or equal to 25 milliohms. And what we see is that the internal resistance typically drops as the capacity increases. Or in other words, as the capacity increases, our test current requirement increases. So on the right here, this diagram shows on the x-axis is the internal resistance, and the y-axis shows the maximum voltage. And the different colored areas show all the different possibilities that you can have for battery testing. For instance, with individual cells, an open circuit voltage of 5 volts is sufficient. But for instance, with HEV battery packs, they may go up to 1,000 volts. The point here is that this is a very, very large range of potential voltage and resistance ranges. So what we find is that when an instrument is focused on its target, rather than trying to do everything, it's focused on its target, the instrument can be more effective and more compact. And as our focus in this presentation is with battery cells, for very large battery cells of electric vehicles and hybrid vehicles, in this red area shown below, the cell resistance may vary from less than 1 milliohm up to about 100 milliohms for the smaller size batteries for scooters and mobile phones and what have you. And one of our solutions is the BT4560 battery impedance meter. It's capable of a fairly high test current. This is one of the major advantages here, is the 1.5 amps in the 3 milliohm range. And with this high test current, we're able to measure effectively very, very low resistances. It also uses the low frequency ACIR method and is able to measure sweep frequency from 100 millihertz to over 1 kilohertz, and is able to generate the Cole or Nyquist plot with the available PC application. It also has a range of different interfaces which can be used for production testing. It can be interfaced with handlers or remote control operation. And again, since its intended target is individual cells, the maximum voltage it can work with is 5 volts. On the other hand, for medium to high capacity cells, where the cell resistance is above 10 milliohms, we have another solution, which is the IM3590 chemical impedance analyzer. And its one of the key features is that now you'll notice the maximum test current is a lot less than the previous instrument. It's 100 milliamps at Vmax of 2.5 volts. And it can measure from 10 milliohms all the way up to the mega ohm range. And obviously that's not, the mega ohm range isn't necessary for batteries, but it is a LCR meter or an impedance analyzer. So it has a broader range of applications, especially for research and R&D. It's also capable of the low frequency ACIR method that we mentioned, where it's able to sweep from 1 millihertz all the way up to 200 kilohertz. And it can display the Cole or Nyquist plot on its built-in display. Again, it's a fully compatible with most production needs, as it has the full range of interfaces. And since it's intended for individual cells, the maximum voltage is 5 volts. Now, end-of-line testing. Now, the requirements here are a little bit different than cell grading, because now we're at the end of the manufacturing process, and hopefully, it's gone through all the different manufacturing stages, gone through many different test ranges, and it's come to the end where we're doing basically a quick test to make sure that it's good to ship out. So in shipping and acceptance line use, generally we use a single frequency. So we get an individual, just a small snapshot of the battery's impedance. And we usually measure at 1 kilohertz. It's a quick approach to mass production testing and acceptance. And so the way we do this is the resistive and reactive components are obtained at 1 kilohertz, but we only take the effective resistance value, or the real component of it, R. And this follows the international standard, the IEC 61960-3, for measuring internal AC resistance, which specifies a test frequency of 1 kilohertz and measurement time of 1 second to 5 seconds. And so for end-of-line testing, our main concern is high speed. And one solution that Hioki has is the BT3562 battery high tester. It has a single fixed test frequency of 1 kilohertz, and it's able to do, it uses the 4-terminal probe method, as mentioned before. its maximum open voltage level is 60 volts. So it's able to not just measure individual cells, but also modules or multiple cells connected together, and has a very wide impedance range of 3 milliohms to 3 kilo ohms. And also it has a range of interfaces for production testing, for instance, RS-232 and GPID. Now for multi-channel battery testing, you know, you may, instead of having, let's say you were testing like 10 sites or 12 sites, you know, it's more cost effective to have a single instrument and test sequentially one after another rather than have 10 instruments. So we have this solution called the SW1002, which is basically a multiplexer which accepts 12 multiplexer modules. Now, it comes with two different styles of multiplexer module. The SW9001, so 12 slots can be populated. When populated with the SW9001, we can have 264 channels of 2-wire or 132 channels of 4-wire. And this is great for end-of-line testing, where we don't necessarily need the full frequency sweep. And we also have a different multiplexer module, which is known as the 9002. The 9002 is also capable of 4-terminal pair method. So it's more suitable for cell grading, where you have to sweep through a range of frequencies. And the board is laid out in such a way that the return test currents and the test currents are arranged so that the effect of the induction error on the sense line is minimized. So if you were to try and create an off-the-shelf multiplexer, for instance, this is going to be a major challenge. It's also capable of, you can have up to 2 different battery testing instruments connected to this. For instance, you could have the chemical impedance analyzer or the battery impedance meter for impedance measurements or sweeping. Or you can have, if you're just doing voltmeter measurements, you can connect a single voltmeter. Or you can also connect the battery tester, the BD3562. So it's capable of connection to more than one instrument, depending on your test flow. Here we have a screen capture from the SW1002's mainframe PC application. And this is basically a demonstration of its multi-site testing capability. So I'm going to play back this screen capture so we can see basically 8 sites of co plots or Nyquist plots being generated sequentially. So we have channel 1, channel 2, channel 3. So every time it tests a channel, it goes to the next site. So although it's not full parallel testing, the speed advantage is clear. So now we have time for a live poll, and I'll read out the questions. So the question is, what is your biggest challenge in production testing of batteries? Is it that test standards are not clearly defined, or there's a fast advancement of technology, or is it cost of test equipment, or is it something else that, you know, you're more than welcome to get in touch with us, because we always want to know about what issues you guys are facing in the field. So if it's not these issues, if it's some other issue, please get in touch with us. We'd love to hear from you. So we'll keep the polling going for a while and see what everybody says. Let's give it a few more seconds. And I will. Oh, okay. So it seems that the cost of test equipment It seems to be the biggest challenge in production testing of batteries. And and as I mentioned earlier, when your instrument is more focused on your target requirements rather than trying to be a generalist, that usually relates to more cost-effective test solutions. So with this, I'm going to hand off to my colleague, Sandro, who will talk about lithium-ion battery production processes and take you through Hioki's solutions.
Thanks, Hassan. Hi, everybody. This is Sandro. Okay, so what I want to talk to, it's about the lithium battery. Then problem that we have right now is because we're getting high volume testing on the lithium ion battery. And since the production increase, we need to, we require more automated test equipment in order to maintain the trend. So module battery pack getting wider, more complex, and more cluster of cells together. So some of them can go up to 100 cells together. Next slide, please. So Hioki brought an innovative solution that strengthened the production line testing. Flying probe converted into ion battery tester. So you see, this is typical for, it's our traditional PC board flying probe tester that we modify it for battery testing. So advantage of that is, of course, we don't need test bed of nails, so there's no investment on fixture. And we are proprietary of 4-terminal probe that detect very low resistance value. So we're also enabled to, capable to do accurate testing of the lithium ion battery internal resistance by adding the BT3562, adding that to the flying probe. Next slide, please. So the concept is of the 1240-61. It's similar to, as I said, the test of PC board with almost the same speed. So that offer very low resistance measurement. So we can check the welding of the interconnection between the intercell. We can go up to a resolution of 1 micro ohms, and that speed up the testing to 2400 cells a minute, and with a high precision probing up to 100 micrometer. So we see the machine on top right. This is authentic. So next slide, please. This one we have a video. We're going to show you a real-time testing from our department innovation center in Japan. And this is a real-time testing. And you're going to see the advantage to have the flying probe and how fast is it to test the intercell connection. So this is a parallel dual probe. So you see right and left, there's 2 probes on right and on left. So they are both testing together. So you can do 2 measurements at the same time. Okay. Next slide, please. So according to all these tests done, we have some data here. So resistance, 400 micro ohm to 40 mega ohm. That measured voltage between terminals, probing accuracy 100 micrometer, and then that allows you to pinpoint into the insulation caster, and we call it casing, and with different angle of attack that allow you more possibility advantage to probe a different location. So score the speed is pretty high. We can test up to 300 cells per minute. And the area of testing of the cell, it's about 20 by 18 inch, but we can upgrade that to another 50% wider by adding a pneumatic slider. Next slide, please. So we also have, of course, design software that is similar to the PCB that we have converted for ion battery testing. So it's essentially the same thing. So we see the top head of the cells with the 14 cells together, and we see some results in the back on the bottom that shows you which cells might be in trouble because it deviates from the other one and will automatically raise a red flag to the operator. So by having the software, we can manipulate the test speed. We can introduce that in production. We can have the LAN connected, and so we can make updates like a colleague last week did the repair online remotely, and he did the upgrade of the software, update the library, and that goes pretty well. Of course, once we get the data, we can get the data in Excel format. So the original way how to do some statistic is very important to check out what is the production trend and if there's something to adjust in the production line. Next slide, please. So, of course, big investment means also big support. In fact, no, the software is so user-friendly, it will do the job for you. So it's gonna tell you which pin is getting near to its lifetime, and usually we replace the pin way before we really need to. We are actually at 2 million touch point lifetime. Shows up on the graphic, we are only at 300,000. On the right side, the software is also user-friendly as far as maintenance, so the end user can replace the pin by himself. It's self-guided instruction. It just needs to press the pop-up button on the window and do the operation correctly. So with a little training, the operator can do that on the floor very easily, and we don't need a master electrician or someone that is expert on the machine to do that. Next. So two different models. We have a -61 and -63 on a compact size. It's pretty much more the same equipment inside the mechanic, but on a compact version, a little bit less expensive, of course. So we have an horizontal slide-in system that is available, or you can have a manual insertion. The slide-in is interesting for production line, of course. As we saw before, we have a 4 movable pin on top, and we can also add an optional 8 pin on the bottom if it's really need to. We're not sure the future of ion battery if we're gonna go on both sides. So some of the specs shows up that we have different variants on the probe angle, so it gives the capability to modify the software, and if you have to make intrusion in a different installation, so it just gives you more capability. So we talk about a 20 by 18 inch testable area with a 50% upgrade with the sliding machine, and inspection speed very fast, so can go up to 40 steps per second. And this is, it tells maximum, but we really improved the test time on top of that. Next slide, please. All right, thank you.
Hey, Sandro, thank you very much.
Yes,
So
sir.
I'm looking forward to the question and answer session, but before that, let me really quickly summarize what we talked about. Get the next slide, please. So we talked about a battery testing at the end of the production line at the EOL. It requires very specialized equipment, so very specialized tests. We talked about the various tests that you can do for measuring the state of the assembled battery, the internal resistance tests. You know, those are not simple resistance tests, but those are complex impedance tests that measure the real and the imaginary value of the impedance over frequency. With specialized test instruments for that, either battery test or chemical impedance analyzers. We also talked about very specific tests that have to be done when you are talking about production. I think we all agreed that lithium-ion cells will be ubiquitous. There will be a huge demand for lithium-ion battery cells, and there will be a lot of testing. So production testing is becoming very important. We showed how production testers can integrate into the overall factory automation process. And we showed one example of a flying probe ATE that is used for high throughput production testing of lithium-ion battery cells in a high production battery manufacturing environment. There's a lot more information available. If you need to get in touch with us, we are located in Plano. That's a suburb of Dallas, Texas. We just moved there in January. We have a very active channel on YouTube where you can see many of the instruments that we sell in action. There's a lot of information there that might help you in selecting instruments. We are active on LinkedIn. We are growing, so if you check that out, that would be great. And of course, Facebook and Instagram is where you can find us. So I'm looking for the question and answer session, and I want to pass the word back to Jennifer.
Thank you, Chris, Isan, and Sandra for the presentation. Great information. So it looks like I'm checking my messages. Looks like we have received 3 questions that came to our actually private chat. So Isan, can we go over some of these questions together?
Sure, yeah.
I think these are some good questions to share with our attendees.
Okay.
So question number 1 is, you have been talking about lithium-ion batteries. I have a Hioki IM3590 and need to measure the internal resistance of lead-acid batteries. How do I do this?
Well, the IM3590 has a maximum open circuit voltage support for up to 5 volts, and so the lead-acid battery, I think, is going to be way beyond that. So you're going to need at least 12 volts and higher. One of the instruments we mentioned, the BT4560, there's an option that you can order which will support up to 20 volts, and that should be able to give you what you're looking for. And I imagine that you want to do a frequency sweep since you're interested in the IM3590. So the BT4560 with the 20 volt option will be able to do it.
Okay, thank you. Question number 2. Right now, I'm using 2 different instruments, one to measure temperature and another one to test my batteries. Can Hioki, as you mentioned in the presentation, also measure temperature?
Now in the presentation, we mentioned 3 different types of tester. 2 of them were able to do the frequency sweep. So they're able to do the electrochemical impedance analysis, whereas the last one was for end-of-line sorting. Now for end-of-line sorting, the frequency is set at 1 kilohertz. So the test time is typically very, very fast. So in general, it's not necessary for the instrument to be able to measure the external temperature. or the internal temperature, because it's such a short test time that it's unlikely that the cell will heat up in that small test time. Obviously, your production environment you'll be able to control. You have many sensors and be able to control the ambient temperature. On the other hand, the two instruments that we have, the IM3590 and the 4560, they are able to measure temperature because they're able to do the whole range of frequencies, and it's more likely that with a longer test time that the cell temperatures will increase. So to answer your question, yeah, we have the two that we mentioned for cell sorting will do it, but the end-of-line testing instruments will not.
Okay, great, thank you. The last question is, the precision of your ATEs is amazing, but the packs on batteries are pretty large. Why do you need such a high precision?
Yeah, you're right. They are pretty large, but we want to basically minimize any kind of variation in the test environment. The more things that we can minimize, more variations that we can minimize, the more there's less things to worry about. For instance, if you were to hit the 2 points where you're measuring the resistance and there's some variation in the distance of those points, that's one area of error that you could possibly have. Another area of error could be that if you're hitting it, your targets at a different force each time. So the precision really helps when you're talking in the milliohm range and nano-ohm resolution. So every little bit helps. So we want to basically minimize, and also the precision of being able to hit the targets. You don't want to hit, for instance, things that get in the way, which could damage the probe tips. So I think that the precision really helps with measuring minuscule impedances.
All right, great. Thank you for sharing your knowledge, Ihsan. I really appreciate that.
Thank you.
And looks like that's all the questions that we have received for this session. So let's go ahead and wrap up. So we just want to say thank you everyone for tuning in. We really appreciate you taking out your time to attend. There is a short survey right after the webinar. It'll take you about 30 seconds to fill it out. So please don't close out your window. And if you can just give us your honest feedback, that will be really helpful for us to host another informative webinar for you. Ihsan, can you switch your slide one more time?
Yeah.
And as Chris mentioned earlier, we do have the third series webinar on August 19th at 1 p.m. CDT. It's about 2 weeks from now, and the topic is maintenance testing of lead acid batteries. And the invitation is in our social media, LinkedIn post, Facebook, and Instagram. And if you need an invitation, please drop us a note and we'll be more than happy to send the invitation to you. So thank you guys for joining. We're gonna sign out. Stay safe and see you next time. Bye.